Hi, my name is Saba, and I'm going to present my research on developing a framework for principal fault displacement, moving beyond the aggregate displacement metrics. Fault displacement is critical for structures that cannot avoid crossing active faults. And previous studies used limited dataset and simplified fault geometry, but the main limitation was that they defined the hazard for aggregate displacement. This means that the normal distance of a structure to the fault and the structural footprint was not included, and the hazard is treated as if the structure crosses all of the overlapping ruptures at once and is subjected to the total displacement. For finite structures, this may not be realistic because these structures can be kilometers away. So first, what are different types of fault displacement? This figure shows part of 1992 Landers event, and the black line shows the primary fault trace, and the displacement happening on it is called principal displacement. In the same event, secondary ruptures can happen around the main fault trace, and these are shown in blue, and the displacement happening on them is called distributed displacement. At any location, the total displacement would be the sum of principal and distributed displacement. And distributed displacement is smaller in amplitude compared to principal displacement. In this research, we only focus on the principal displacement. The location of displacement can be defined using two coordinates: a long strike location on u-axis and a strike normal location on t-axis. A long strike location is the position of displacement along the rupture segment measured from one end, and when normalized by surface structure lengths, it would be relative along strike location. And a zero value shows at one end, and a 0.5 would be in the middle. The strike normal location is the perpendicular distance of principal displacement to the fault trace. In this study, we used FCHI dataset, which includes more than 40,000 displacement observation from 75 events, and it covers magnitude between 4.9 and 8, including all styles of fault. It also distinguishes between principal and distributed displacements. This figure shows the summary of the dataset. The upper figure shows the distribution of relative distance along the fault, and for moderate to large events with magnitude between 6 to 8, the observations span over the full along the strike extent of the rupture. And the lower figure shows the distribution of normal distance to the fault. And with increase in the magnitude, the normal distance to the fault also increases. This means that in larger events, principal displacements can happen kilometers away from the fault. At any along the strike location, multiple ruptures can be present. For example, in this part of the Landers, two ruptures are present, and these are called overlapping ruptures. However, the displacement is not always available at these overlapping ruptures. For example, the red dot shows the available or the measured principal displacements. When displacement is available on one of the ruptures and missing on the other one, we need to estimate the missing one. And in order to do that, we assign zero displacement at rupture ends, and we interpolate the missing displacement in the rupture using the available displacement on that rupture. This step is necessary because we want to define the hazard for individual principal displacement or the displacements that are crossed by the structures. So for that, we need to have the displacement available on all of these overlapping ruptures. So aggregate displacement is the sum of individual principal displacement happening on individual ruptures. And defining the hazard for aggregate displacement would be the case where the structure crosses all of the overlapping ruptures. But since these ruptures can be kilometers away, aggregate displacement may not be the exact displacement demand. So we need to convert from aggregate displacement to individual displacement. And for that, with having the model for aggregate displacement from previous work, we need 3 steps. These are the number of overlapping ruptures at each location, the amplitude ratio of the displacement, which means how the aggregate displacement is distributed among the overlapping ruptures, and the normal distance to the fault. And with these 3 components, we can convert from aggregate displacement to individual principal displacement. So the previous framework defined the hazard for aggregate displacement, which is the case similar to the purple structure that crosses all of the overlapping ruptures. And for this, the formulation is defined as the summation over all possible scenarios using the event rate, the probability of surface rupture happening, the probability of not being in the gap between segments, like in this figure, and the probability that the aggregate principal displacement is not 0. And the last component is the probability exceedance for aggregate displacement. In this research, we want to define the hazard for individual principal displacement, which would be the case of the actual ruptures that are crossed by the structures similar to the blue one. And for that, we need to change the final component into the probability exceedance for individual displacement. And this probability exceedance includes 4 components. First one is the model for aggregate displacement, which we have from previous work. And the other 3 components would be the number of overlapping ruptures, the amplitude ratio, and the normal distance to the fault. In the next slides, I will describe the models we adopted for these new 3 components. The first one is the number of overlapping ruptures. Since in most cases we observe only one number of overlapping ruptures, we use the mixture model. A Bernoulli distribution for the probability of seeing only one number of ruptures, and a Poisson distribution for having more than one number of ruptures. And the probability of having more number of ruptures increases with the magnitude of the event and the curvature of the fault. The curvature of the fault is a proxy for the geometry of the fault, and it describes the degree of bending or the directional change relative to the fault trace. And using these 2 components as the predictor for number of overlapping ruptures, this figure shows an example of how well our distribution fit the data for stripy slip fault with magnitude above 6.5 and log of curvature below -10. The second component is the amplitude ratio of the displacement, which is the ratio of individual principal displacement divided by the aggregate displacement. And because ratio is between 0 and 1, we used a beta distribution. As the number of overlapping rupture increases, the aggregate displacement would be divided into more number of ruptures. And in order to account for this effect, we constrain the mean of the distribution to be equal to 1 over number of overlapping ruptures. The second component is magnitude. With increase in the magnitude, the spread of our distribution decreases. This means that for the same number of overlapping ruptures, an event with larger magnitude would distribute the aggregate displacement more evenly among the overlapping ruptures. And this figure shows how well our distribution fit the data for an example of normal and reverse fault with 8 number of ruptures. The last component is the normal distance of displacement to the fault trace. However, defining the fault trace is not straightforward. And to account for this uncertainty, we define 3 alternative definitions for the fault trace. The first one is the segment coordinate system, which we assume a single straight line as the fault trace for each segment and measure the normal distance of displacements to this fault trace. The second one is the random fault trace, which is useful for the cases where there aren't enough information on the exact location of the fault trace. So for that, we assume one of the overlapping ruptures is the fault trace randomly. For example, in this part of Landers, there are two overlapping ruptures. In the first case, we assume the right rupture is the fault trace, and the displacement in this rupture has a zero normal distance, and the normal distance of displacement on the left rupture is measured relative to the right one. And in the second case, it would be reverse. And the third approach is the maximum principal displacement trace, which in this case, there are more information on which of the overlapping rupture has the largest principal displacement and is more probable to be the fault trace. For example, in this part of the Landers, this right rupture is the fault trace. These three definitions of fault trace leads to different concentration of data around zero and different spread of the data. So we used three different distributions, which are single or mix of two-student distributions. Even though we need to use three different distributions because of the three different fault trace definitions, the spread of the data shows a similar trend. With increase in the magnitude, displacement can happen at these distances further from the fault, but the larger displacement happen closer to the fault. And in order to remove the effect of magnitude in the amplitude of the displacement, we normalize them by the average aggregate principal displacement. And this figure shows an example of how well our distribution fit the data for strike slip faults with magnitude above 7.25 and normalized displacement above 1. So with having these three new components and the aggregate displacement model from previous work, we can now describe the probability exceedance for principal displacement, which is equal to, for any possible number of overlapping ruptures, how the aggregate displacement is distributed among these overlapping ruptures, and which combination of these ruptures our structure will cross. So the International Atomic Energy Agency benchmarks are widely used by previous frameworks to evaluate the hazard for fault displacement. And here we use them to compare our proposed framework with the previous one. In this figure, for one of the cases, we are comparing the hazard for aggregate principal displacement, which is the blue line, and the proposed framework, which is the black and the red line. The red line shows the case where our structure crosses only one of the overlapping ruptures, and the black line shows the case where our structure crosses any combination of overlapping ruptures. The key observations are that the aggregate displacement, or defining the hazard for aggregate displacement, the blue line, is the upper limit, and most of the hazard for the case where the structure can process any combination of ruptures, which is the black line, comes from the case where the structure will cross only one of the overlapping ruptures. And this highlights the difference between defining the hazard for aggregate displacement and defining the hazard for individual principal displacement, which in this case, it would be the actual ruptures that are crossed by the structure. In this case, we want to show the uncertainty associated with the different trace definition and the location of the structure. So we define two structures, one centered on the fault and one only on one side of the fault. Because ruptures would happen on both sides of the fault, the structure that is only on one side of the fault, which is the red one, would be subjected to only part of the ruptures. And it will be also subjected to a smaller hazard. This effect is stronger for the second and third cases of fault trace definitions, which are the maximum principal displacement trace and random fault trace definition. And this is because of their smaller spread of distribution. This slide highlights the difference between the previous framework and the proposed framework, which can account for the uncertainty related to the fault trace definition and the location of the structure. In the final comparison, we want to show the effect of the structural length and the distance of a structure to the fault. So we assumed 5 different structures on different location from the fault and with different structural lengths. Longer structures and the structures that are closer to the fault would experience a higher hazard, but the proximity to the fault is the dominant factor. So the final remarks of this research is that we define a physics-informed PFDHA framework using a larger data set and more complex fault geometry. And this framework defines the hazard for principal displacement, which is the actual ruptures that are crossed by the structure. And it also is capable of accounting for the uncertainty related to the different definition of fault trace and a structural length. We are also developing a similar framework for distributed displacement right now. Thank you.